Hello. Hello. I'm very glad to be here. Thank you so much for inviting me, the Taiwan Geothermal Association. My colleagues are here as well. The first is myself at Lawrence Berkeley National Lab. Just to mention for a moment, we have 40 people working on geothermal. I don't even know what they're all doing. Sometimes I go to these conferences, I find out things they've been doing and they know about. But it's a very enriching environment, very enriching, lots of input, lots of discussion and debate. My colleagues are Steve Jarpy and Joel Jarpy, a combination of electrical engineers that make equipment and process data for us. And you'll see in a few minutes that we have massive amounts of data, as always in the modern world. Am I speaking well enough? Can you hear me back there? Processing data, getting large amounts of data, as you heard earlier, it's the same. It's just getting more accuracy, more resolution, more detail. And that's what we want, and fast, so that's part of that. Then we have our college collaborative university, Northern Taiwan National Ocean University, Professor Lee here, who is also the president of the Geothermal Association. So we get some inside advantages for that. And then he has his associates, Xiaocheng Wang, and then students Kai Chen and Xinyu Shui. So these are the people that we work with. We've been working in Taiwan now for almost 5 years. Almost 5 years. Programs that I'm retired. I'm getting tired, that's for sure, but I'm not entirely retired. But we were given a charge a long time ago now. When the bombing came in, there was a major economic collapse. And actually people were beginning to get worried about global warming, at least in our country, at least the liberals were. Conservatives pretend it doesn't exist, but that's a different story. And so we were given a fair amount of money from the Obama administration to make geothermal assessment more productive, faster, more accurate, and make it easier for operators to get the information they need to improve their decisions for developing a geothermal field. Interestingly enough, we got a lot of interest in the Philippines and a lot of interest here in Taiwan. Not much interest in the U.S. I'm not sure how many people are working with people in the U.S., but we almost have too many PhDs. They're all competing against each other, and if you have something new that infringes on my territory, I'm going to ignore you. But we found people overseas are very interested, and so we're starting to develop and apply our methodologies overseas. But I will point out some more things regarding that. So here's where we're situated here. This is San Francisco. LBL is here. It's very close. Up here is the guys who have the geothermal field in the world. 100 years of development. We drive there in about 2 hours. In this study I'm going to talk about, we treat the geysers as we treat the geysers as an outdoor research lab. There's so much known about this field that we can use it to our advantage to learn about geothermal reservoirs, to learn about how to identify geothermal reservoirs, and then we can take it and transport it to other places where there's no knowledge, nothing. And that's what I wouldn't say that, I hate to say that here in Taiwan, but they don't know a lot. They know they have heat, but they don't know a lot about the subsurface. It's a steam reservoir, and right now we have 200 instruments operating in the geysers at the surface to record micro-earthquakes. Micro-earthquakes occur about 50,000 a year at the geysers. And we have 200 instruments, so we have an amazing abundance of data. Just a little bit about the geysers. It's the largest geothermal field developed in the world. The 1.5 gigawatts of power, it produces 6% of the electricity for California, this one field. And that might be a paradigm for northern Taiwan. That's why we got interested in some of the issues related to northern Taiwan, because Whereas it's been developed for 100 years, 22 power plants, there's almost nothing in northern Taiwan, but it could be this in a period of time. This is a model of the geothermal reservoir. The reason I'm pointing this out is that all these wells, because of all these wells, these are all wells that have been drilled into the geysers over the years. Because of that, this is the actual reservoir model down here. The reservoir is actually in here. This is the heat source. This is the fell-site intrusion beneath it. And then up in here is where the reservoir is. Almost know everything about that reservoir. We know where the steam is, we know where the water is, we know where the fractures are. We almost know everything about that. So we use it as a lab. So what can we test? What's an hypothesis we can test? What's information we can see if it's valid as we get it in our methods? So our method we've been developing, like I said, it was a call to arms from Obama. What can you do to make geothermal more effective, faster, more accurate? Well, I'm a seismologist, so I went to look at seismology, but the problem we had in seismology was instruments cost a lot of money. So, and our concept was we wanted a lot of instruments, higher resolution, high more detail, and I'll explain later in a short amount of time. The instruments were expensive. I'm going to shine the light on this guy over here. He invented what they call the Jarpy box, $300. It compares to a Geralt, $440,000 Geralt. It's a genius, okay? And before, we were limited in doing geothermal studies by the cost of the instrumentation. 10 instruments that overwhelmed your budget. Now we put in 100 instruments in that location, no problem. Okay, so what is tomography? The tomography is you have earthquakes at some depth. Okay, first off, I just clarify right now, you don't do this without earthquakes. That's why it works so well in Taiwan. They have enough earthquakes to last forever. And so the whole Pacific Rim of Fire has earthquakes. But we have to have an energy source. An energy source is below, we want to know what's going on in here. And the earthquakes are popping off down here. So they have to travel through our reservoir to get to us. And like I said, we have maybe 25, maybe 50 instruments up here. And we may have 200, 300, 500 little tiny earthquakes down here. And every one is traveling a different little pathway to get from its earthquake to all these stations. So what we do is back project that with a developed method, tomography. The image, what is in here that can explain all that data? And I'll show you later. It's not a matter of guessing and trying to get it right. It's a matter of, there's so much data that it averages out your uncertainties. It finds the mean. Even with fairly poor data, when you have 50,000 samples of the volume, it begins to peak out into the average, which is more than the norm we want to know. So what do we get from this? What kind of things are we trying to determine from the tomography? Okay, what we get is a velocity, we call a velocity model. So the energy comes out of here from an earthquake. It comes out of a P wave or an S wave. Right? Everybody knows that. Right? So we record the P wave and the S wave at the surface. But how did it get there? What's the speed it had to travel to get there? And what speed did it have to have in what part of the volume? For example, over here, right here, for example, it had 500 earthquakes down here, all passing through that little spot, recorded at 100 stations up here. There's almost no way you can artificially modify that and not have to satisfy all those little travel paths, 25,000 of them. And it also has to be consistent with the model over here. So this consistency of all these points in the model have to all be consistent, and that's what the tomography mathematical method forces you to do. The other thing we get is attenuation tomography. And that is when it pops off with an earthquake, it starts off with a small amount of energy, and it shows up in the amplitude and it starts off with a little amplitude of the wave, and as it propagates, it starts losing its energy. That's attenuation. And it's the same thing. The attenuation has to be the same at this point for all rays that pass through that, as over here, over here, over here. So what we end up with is a volume, typically a volume, in this case, for example, 5 by 5 by 5, maybe down to where the earthquakes are, maybe 5 kilometers deep. So it's almost like a volume, and inside that volume is the model of the reservoir we want to understand. I have to get some liquid. I might have to try it now. So. Okay. Our problem is in geothermal, nobody's ever done what we've done. What we've done is model these parameters of velocity. We model these parameters of velocity and attenuation. It looks like that. And we want to interpret the images we get. You'll see soon. You'll see some images of reservoirs, and they have different parameters depending on what you obtain. You'll have a velocity model, so it might be high velocity in one part, low velocity in another. It might be high attenuation in one part, high attenuation in another. And then there's the rock physics parameters we derive out of those, which are 5 rocks. So these are 4 parameters: attenuation, velocity, and we derive elastic parameters, which is 4 of those. And there's been a lot of work done in the oil industry interpreting these observations. A block image of your volume with giving you where the values are high, where they're low, what the shapes are. But that's the oil industry. It's a completely different story for geothermal. That was all sedimentary material mostly in the oil industry. This is mostly volcanics or metamorphosed rock. But this is what they've come up with. There is this here, but for example, one of the parameters we derive is Poisson's ratio. Poisson's ratio is a good indicator of fluids. Generally, it's been found in samples in the lab. High water content will be high Poisson ratio. And this is the big baby I'm looking at today. The very low Poisson ratio can indicate steam. There's other values in between. What's going on? Values in between. So this is the kind of thing we want to do for geothermal. You'll see this soon. You're going to see images of the subsurface and different values for these parameters, like Poisson's ratio. And we want to be able to say, look at this low Poisson ratio in this portion of the field, that's probably steam. Look at this, a very high Poisson ratio in another part of the field, that's probably water. And then in the middle, in the middle, it may be just background normal geology. Okay, so we're trying to develop these relationships for geothermal. A lot of them will transport geothermal from oil and gas, but we want to improve on them and validate them. So here's our experimental field, a slice out of the geysers. Okay, so let's be clear what we're looking at here. This is a cross section of the geysers geothermal field. Like I said, we know what's down here. This is just the wells we're showing. So this is what was called the gray wax. This is the steam reservoir here, right here. We know where the steam reservoir, we know where the entry points of wells are. We define this boundary pretty accurately. We know where the steam is. Down here, we don't know a lot about this. We know where the top of it is. This is the intrusive granitic well site that's heating up, cooking the field. So this is your, I'm sorry about that, folks. I didn't do that. Okay, sorry. And I'm also still talking, okay, I keep moving my microphone. We're okay. So we know what's in the field, and it turned out to be an opportunity here that we took advantage of to run an experiment. What we did here was, there's these 4 wells. They're drilled all the way down. We know where they are. 4 wells. They go right through the whole system. And down here, they go into the really what we call the hot zone. It's 400 degrees C down here. And they go right through the steam zone here. So what happens is that this well here was a brand new pristine well. Never been used, just drilled. And they're going to start pouring water down the well. And so we know right here where it's going to happen, when it's going to happen. We're going to examine what happened. That'll give us some control and understanding other systems where we don't have this kind of knowledge. And it turns out that every one of these wells has a flow history. For this one, for example, was very low flow rate, and then it ramped up really fast at the beginning of our study. This one has been going up and down in flow rates, or the water flow rates, for years, and this one is similarly. So let's see what we did with the tomography. So this is a cross-section image of tomography at our coordinate system, which is going north and south, like halfway through the volume where that cross-section was. And this is the top of the steam zone we showed. And here is Poisson's ratio. So we know there's a steam, so what are we getting for Poisson's ratio? So we're getting about 0.2. And what are we getting from bulk modules? This is one of our rock physics parameters we derived. So bulk modules down here around 20. This just theory is that it's for a steam zone, you have a fairly low bulk modulus and you have a fairly low Poisson ratio. So that more or less validates the theory that we've read about and saw in other studies, and it validates where we know there actually is steam. I'm sorry, I'm being too old to do this. Okay, so here's another cross-section of our fields with our tomography. Remember, we fill the whole field up with detail. A 5 by 5 by 5 kilometer area. Five by 5 by 5 kilometer area. So here's the cross-section where those wells are. Okay. And we did here, we did 30 days of tomography for 30 days before any water was released in this well right here. So it's so pristine. The second 30 days, water was injected in this well. Okay. What's going on here? So this well here, like I said, well, first off, let's look at what we're looking at here. So this is the steam zone in here. Green is steam. Light blue is normal Poisson ratio, like normal dry geology, and dark blue is water. So these are water pockets in the volume. This is steam in the volume. And the other light blue is more or less normal geology. So look at the bottom of the well, we see this blob down there. We see this blob down here. When it's sort of injecting water. Okay. So before that, it's actually an average geology, light blue, average geology, normal geology. No water, no steam, just average geology. Suddenly, Poisson ratio dropped almost zero when water was injected, right at the bottom of the well. This well, they've been here for a while, but they ramped up the production of installation of water, and it creates all these little earthquakes. You can see coming right out of the well. Clusters of earthquakes where the cold water is hitting hot material, forcing the earthquake. This guy here, he had been quiet for a while, and earthquake was way down here, and not a lot was going on. They more or less recent kind of stability. So when they ramped up the injection in advance, it started having the reaction of water into a hot zone again. See, by this point, water boiled into steam, so it was steam down here after a period of time. But if you start putting cold water in there, bam, you can see what happens there. You drop place on temperature right away down to 0.5. And we're going through that. And this is other people's research and engineering at Paron. We're the only other group I can see that's actually pursuing understanding these kinds of tomography results to identify steam. So they could identify steam here very low BP, very low PS, and steams over here. All right, so now we're going to apply this to Taiwan. The reason we look at steam, we try to understand how to see steam, because in northern Taiwan, the tectonics in Taiwan are pretty interesting. We have this whole Pacific plate subducting over here, the Roku Trough, a series of volcanoes that come off of the backside of the subduction. Then we got the China Sea and the Philippine plate subducting over here, and Taiwan is in the middle, and there's a series of volcanoes right across here in northern Taiwan. It's kind of the ideal place to develop geothermal resources. Time's up already. Okay, come on. He did the talk before, we took twice as long. Come on. I'm going to wrap this up. Okay. So, quickly, there's a lot of resources in Taiwan. You've seen all these slides before. There is all these hot springs in Taiwan. There's lots of geothermal, and we're hypothesizing that we could push these instrumentation through some of these zones with a high likelihood and get a better image of what's going on for Taiwan. So this is northern Taiwan. This is the okay, so these are instruments we have in northern Taiwan, and we're limited to not going into the park right now. So we're looking at the edge of the park, the volcanics of the park, and volcanoes over here, there's volcanoes over here. So we hypothesize there could be a lot of steam in this area. It's very low, very highly acidic, corrosive water, so it's very difficult to develop for geothermal. But if there are steam pockets, steam reservoirs, that may be the way to go. So we looked and did a tomography, and okay, I'll pause here, but this is a 5 by 5 by 5 kilometer area that's deep, and we're looking here at the Q attenuation of P waves in our volume. And what I'm only showing what's a very low QP. You can see it was not modeled in these two holes here. Most of it is low QP. There's two cavities where there's not low QP. And over here, we're modeling, forget already, bulk modulus, and it's saying here we're looking at average bulk modulus. The point here is that attenuation tomography is seeing the same thing as travel time tomography. They're completely independent parameters. You get the same answer from two completely independent computer runs. There's a validation of the method for one thing. So, but what about these two cavities that we see here? More or less normal geology around it, although very low QP. Okay. So let's look at Poisson's ratio. We again see the same cavity with Poisson's ratio. Two cavities here, and this is normal Poisson. So you can say this is normal geology all around this. But what's in A and what's in A and B? Okay, let's go look. Okay, it looks like B fills up with very low Poisson's ratio. And A fills up with very high Poisson's ratio. From the studies we did of the geysers, that would indicate that this is steam, this is water. So we project that there's two reservoirs here, one is steam and one is water. Just isolate those out, pull those out, look at them in separate. Okay, so this is the low Poisson's ratio, and this is the high Poisson. So this is your steam reservoir. This is your water reservoir. I would propose that these studies aren't expensive. We've automated so much of it that if you're doing conceptual models, you might want to look at this kind of thing to get better fix on the details of your conceptual model. That's the end of my talk. We do a lot of validation tests. We have a good outdoor living lab to do validation tests. Having these two independent parameters get the same answer, we see that over and over again, gives us a lot of confidence in our results. We use a lot of rock physics to interpret the reservoir conditions. It provides a good way to characterize the porosity, permeability, the location of fractures, and the water content. So it's very effective. The best way we found to identify the state of water is through Poisson's ratio, which we showed a lot, and we found steam and liquid reservoirs. Thank you.